basically that's that will be the whole thing. Now that's why I assigned the homework. I sent it to Amber. I think Amber is going to upload it on the Canvas. So the homework has 6 problems. I recommend you to go for the 6 problems. So basically those 6 problems are very, very important for the midterms, you know, and in the midterm, we will have like mostly the problems. And then in the next class, I'll assign the project 1. And I'll make the project 1 due not midterm, after midterm, which is the October 11th. But I think the materials that we're going to cover up to that level will be pretty helpful. Okay.
So the midterm will be on October the 3rd?
Midterm will be the October the 3rd.
Okay.
October the 3rd or October the 4th. Our regular time is October the 4th. So I think I need to take the midterm on October the 4th.
Okay.
But the midterm will be, I'll assign the midterm. I can make it like virtual, like take home. So I can assign that the midterm, but that has to be done. I cannot give you the whole 24 hours for the midterm, but I can allow you, like, I can open it by 5 and it will be due by 10 or midnight, you know? So I can do it like that. Because I think the regular time of the class is the Wednesday, and I need to take the midterm on Wednesday. All right. Okay. So basically, I need to share my screen. I have some background noise. If you hear the background noise, just let me know. Okay. If you're not listening in a background noise, then it's fine. Are you hearing the background noise? No. Okay. Interesting. I'm hearing lots of noise. Okay. So basically, the first thing I want to cover today is the applet force, you know, under a structure. So there's gonna be the applet force under a structure. But before doing that, I also wanted to cover the equivalent permeability. So the equivalent permeability, I am going to post these on Canvas. So basically, the question is, let's say we have series of soil. Okay, let me explain the problem here. So the problem is, let's say we have a layer of soil. You know, so each of the soil has a certain, these are X and this is Y. So let's say we have a soil layer 1, 2, 3. Okay. So let's say we have different soil layers. The soil layer 1 has a permeability of KX1, and along the Y direction is the KY1. Then it has the permeability KX2, KY2, and KX3, and KY3. Okay. So looking at all those permeabilities, now we wanted to make sure like how it will flow through. So we wanted to find out, like, let's say we wanted to find out a equivalent soil. So converting all 3 different soils into one soil, one representing soil, you know. And for that soil, we wanted to find out like what is the overall KX, what is the overall KY, and what is the overall K. Any idea?
So is there a formula we used like to? a general formula to make them all as 1K, or we take average, or how we do?
Sure. Any idea? I'm asking. I'm gonna discuss it later. I wanted to know if anyone knows how to do that.
Okay.
Yes, the hydraulic gradient will be same.
Hydraulic gradient will be same. Okay, so
Like it's like
go ahead. I'm listening.
equivalent K. We are
Yes. So how to calculate the equivalent K? What is the criteria to calculate equivalent K? Any idea? Okay. So basically the idea is we have to look at the flow. So if we know the flow, let's say we have a Q, we apply Q, certain Q. So let's say we wanted to find out the KY, then we can inject the water vertically. So what's going to happen? The Q will be same for all of it, right? But between these two, there might be some potential difference. So basically, along this process, the Q will be same. The same Q will flow through. So if you know that what is the flow along that layer, we can find out the equivalent K. That's one way. For the vertical K, for the horizontal K, if we give a Q, then what's going to happen? The Q will be divided into 3Q, Q1, Q2, and Q3, right? 3 different layers. So it will, some part of Q will pass through the layer 1, some part of the Q will pass through layer 2 and layer 3, right? So can you remember in the circuit how we do that?
yeah, in series connection, the current flow I is remain constant.
In series. So
yes.
right here in this direction is series, right? For us. So in this direction, this is series.
Yeah. So
right?
Q is constant.
Series. Q is constant. So I is constant.
Yeah.
Right? So if the
Yeah.
I is constant, then the other things, what is the potential difference? Is changing.
These are changing.
Right? So the voltage is changing here, the potential difference is changing. And in the parallel connection, what happened?
Voltage difference is constant and current flow is different according to the path.
According to the path. So in this case, we will have a H1 and H2. So pressure difference, right? So the pressure difference will be same. And in between that pressure difference, it will be distributed, right? So basically, that's how we find it out. So let's just go ahead. Where is it? Is it here? No, right here. Sorry. Yes. So basically, if we wanted to find out, we have the different layers. We have a certain Q, right? And within that Q will have a component of Q1, Q2, up to Qn for different layers, right? So let's say we have the KH and KV. KH is the along the horizontal direction. KV is the K along the vertical direction, which is like X and Y. So in this case, for the parallel connection, what's going to happen? Our H, there will be a hydraulic gradient that's going to be constant, right? So how do we derive the I? What is the I? Q equal to KIH, right? Or KIA, but here we are considering unit length, so we're just saying is QIH. So basically our total Q is a part of what? Is the equal to Q1 plus Q2 plus Q3, right? Plus all of it up to Qn. So basically Q equal to, if we have the unit I, so basically it's going to be like KH right? It's all the KH. So if we consider like it has a unit hydraulic gradient, then our these numbers Q becomes KH, right? Equivalent. So it's going to be the part of K1, K2, K3, or you can also take it like I is there, but your Q will be Q1, so this one, right, plus Q3. So basically you get, where is it? Oh. Wait, how to erase it? Okay. Okay, so let's say we have the equivalent Q is the total Q equal to Q1. So equivalent Q equal to K E equivalent I H, right? And so basically it's going to be like K1 I H1 plus K2 I H2 plus K3 I H3 and so on, right? So I will be taken out from both sides. So basically you'll have the KH is basically the summation of the KH. KE equal to summation of KH. So from there we can find out like the K equivalent is this number. This is for the horizontal flow, KH along the horizontal line. Okay. Now we need to find out like what happens in the vertical direction. So in the vertical direction, what is constant? Flow is constant, right? Q is constant along the vertical direction. So in the vertical direction, what we have? What is the Ki? You know? So if Q is constant, what else is also constant? Any idea? Q is what? The flow rate, right? The flow, or in the same area, the flow rate is constant. Q equal to AV.
AV.
So A is constant for all the sections. So the V is also same, right? So basically now what is V? V equal to Ki, right? So V equals to Ki. So in this case, V is constant means our Ki is constant in every flow, right? So the summation. So basically, if the Ki is constant, what we have to do is our Ki. So basically, on that part, if we take the IH, what is the IH? This is the total head loss. You know. So what is the head loss? Let's say we have a layer, 1, 2, 3 layer, right? So Q is constant. So basically Q is constant means V is constant, right? But between each layer, they have a drop. What drop they may have? What we may have? What happens in the flow line? When the soil passes through, when water is passed through the soil, due to the seepage, what happens?
Energy loss.
Energy loss, pressure drop, right? There is always a pressure drop. So that pressure drop will be what? You have a potential difference, right? So what is I? Do you know what is I?
Hydraulic gradient.
Hydraulic gradient. How we calculate the I?
Del H by del L.
Del H by del L, right? Or del H over L. H is the head versus the L, right? So let's say we have some kind of soil in it right here. Okay, so in this case, we have the water and in between we have the soil, right? So in this part, we have the soil. Now we have a height difference, H, and here we have a length different L, right? So what is the definition of I? Hydraulic gradient equal to H over L. right? That's the definition of the Hadley gradient. So then what is H? So if we want to find out the H, what should it should be I into L, right? So I is the Hadley gradient multiplied by L, right? Okay. Now, what is constant in this flow? I, right? I is constant. What is changing?
H.
H. So basically what happens, our H is changing. So in this case, our H is equal to, so in this case, sorry, it's a pressure flow, not a series. This is a series connection. So basically we have a total potential difference. So we have a Hadley gradient I, and this I is divided in I1, H1, I2, H2, and I3, H3. You know, it's divided in 3. Why? Because we have the loss, right? Potential loss. So let's say from point A, B, C, D. So from point A to D, we have a pressure loss of IH. Our thickness is H, which is the length. Here H is the length, not this H. This H is the head difference. But right here, the H is the length, is the thickness of the soil layer. And that H is equal to H1, H2, and H3. Okay. So then what we will have? We have the hydraulic gradient, or the pressure drop is equal to IH is the total, right? Is going to be equal to I1, H1, I2, H2, I3, H3. All right. So then, so the total pressure head is equal to the sum of each drop, right? So if our head difference is IH, it will be, or this is the total drop between point A and D, is the IH, this is the total drop. This drop will be equal to the drop between A and B, B and C, and C and D, right? That's the total drop. So basically, we are getting IH equal to I1H1 plus I2H2 plus I3H3. Summation of all the drops, right? That's the total drops. So now I equal to what? What is V? V equal to Ki.
V over K. V over K.
So this is V over K. I equal to V over K. So the first I equal to V over K, V over K1, V over K2, V over K3, right? With multiple H. So the V is common, so V will be out. So basically we get 1 by H by KV. So your final equation is going to be this, where your K equivalent is basically H common for all of it. So we had like K over H, you know, that's how it is. So it just, that's the final form of the equation. We have K, H over K is equal to H1, KV1, H2, KV2, H3, KV3. So you just flipped it and make it a good looking equation. Looks like this. That's it. You know, I'm not going to the detailed derivation, but you need this equation. That's one. And then you need the other equation. What is the other equation? That's two. These two are extremely important equations, even for your PE. So you'll get one exam in the PE on this. Equivalent K. Very common problem. So we get our KP and KH. Okay. So this is the KH. And this is our KV, right? Now my question is how we are going to get the K. How are we going to get the K? Any idea? We got the equivalent KH, equivalent KV. What is the K? How we calculate the K?
K root over K H square plus KV square.
What?
Pythagoras formula.
Pythagoras
No.
formula?
No. It should not be.
Should not be, right? Okay. It's a vector. So how we can calculate the K?
A parallelogram theory.
Parallelogram theory doesn't work here. Okay, remember it. K equal to root over KA, KH, KV. That's it. Okay. Okay, so that's our part one. I wanted to finish. Any question on this? Any question on this?
I have a question for not just
Sure.
at the beginning when we have
Yes.
Q from the top. Why we have KY equal if the soil are different?
Why we have Q equal? Because
I mean,
the
if
flow
we
is
have
same.
if we have vertical Q, so why the
Yeah, so
KY is-
your flow is constant. Your flow is not changing, no matter what.
but the I don't get the connection between the K and the Q.
Okay, the connection between Q is your flow. Q is your
Okay.
flow.
But K is the permeability coefficient, right? Which is
K is
different.
the permeability coefficient, which is different. K is the resistance, basically. K is your resistance.
Yeah, but I know. But why? I mean, KY is equal for the three soils, like soil 1, 2, and 3.
Yes, K is equal to. I don't get your question.
So
Say it again.
the beginning you said like if we have
Yeah.
Q.
You have the Q. Q is constant. Yes, Q is constant. Here is Q. Q is constant. The flow is constant. Q is flow.
But that does not mean that KY equals KY2 equals KY3, right? It should
No. It's different. It's absolutely different. If your KY1 equal to KY2 equal to KY3, then you just have only one K. You don't need to do any calculation. You already have it. Why you need to do that?
Yeah, I was just confused. I just mixed up things. I'm sorry.
Okay. Yeah, that's fine. No worries. So is it clear now?
Yeah, it's clear now.
Okay. So basically, we have one part Q is constant, the other part Q is split. You know, the other part is your potential difference is constant. Like between these 2 points, head difference is constant.
Yeah.
Okay, good. Now give me 1 second. 1 minute. Okay, all right. Now, let's go back to our discussion from last week. So, can you remember our flow net calculations?
Some of it, yes.
Yes.
Why some of it?
I mean, not all of it, but yes, I remember some of it.
Okay, today today I have a bullet train. So I'll cover so many things in a very, very short time. So I'm not going to go slow. You know, if you need to stop me, stop me. But I'll just give you another recap. So let me try.
I mean, if you want to solve a problem on it or no? We solved the problem last week, right?
Yeah. I'm not gonna solve the problem. They're just gonna basically I'm gonna go over the problem in the book, but I just want to give you the recap so that you can remember what basically we have, you know. So you don't get lost. If you get lost, then my time is not useful. Okay, so basically, let's say we have a soil layer here, you know, and within the soil layer we have a sheet pile. And now in this one, we have, let's say, some water. So we have a water here. And then we have another water table here. Okay. This discussion is very important for our class today. So I'll just go over it. So this is our bottom layer. Load this up. So this is our bottom layer. Now we need to find out a few things. First of all, we have to develop the flow net. Okay. So what happens on the flow net is we have a head difference. So let's say our head is H. So our head is H. So within that H, what will happen? Water will pass through the soil, right? So when the water will pass through the soil, we have a flow line. So what is our first flow line? This one, all right? What is our last flow line? The bottom line, right? That's our last flow line. Okay, and then we also have the equipotential line, which are the drops. And the idea is the flow lines and the equipotential lines will connect at we will cut each other at rectangle or right angle, right?
Yeah.
So basically what we have here is we have our first flow line, and then we have our second flow line. We have our third flow line, and so on, right? And then the other way, we'll have on the other hand, we'll have our equipotential drop. So our equipotential drop will cut them at right angle, like this, like this, like this way, kind of like this way. It's not very perfect, but this is how it is. Now, what is common within a flow net? Within the flow line, so how many flow lines we have here? How we calculate the flow lines? How many flow lines? Number of flow lines, NF, right? We have a NF. So what is the NF? Our number of flow lines is what?
4.
So we have one flow line, right? We have second flow line, and we have third flow line. Okay. So NF equal to 3. And then we have the number of drop in D. So how many drops?
4.
8 drops.
So we have 1 drop, 2 drop,
8 drops.
3 drop, 4 drop. Then we have 5 drop, 6 drop, 7 drop, 8 drop. Okay. We have 8 drops. All right. Now, within these drops, one line got deleted. I don't know how. So basically our ND is 8. All right. So now let's say we know our H equal to 8 meter. That's our height difference. So what is the water pressure or potential head H here equal to 8, right? So we have 8 drops. So through each drop, what is our drop in the pressure?
1.
Is like 8 meter, which is H divided by ND, number of drop, right? Which is 8. So I intentionally pick this number. So this is 1. So our each drop is 1 meter, right? So basically what happens is H equal to 8 here, H equal to 7, H equal to 6, H equal to 5, H equal to 4, H equal to 3, H equal to 2, H equal to 1, H equal to 0, right? So that's how our drop is coming up, right?
Yeah.
Now, what is the meaning of it? Meaning is along this line, our pressure is equal and the pressure is H equal to 7. Along this line, any part of this line, right? Along this line, our drop is 6. That's constant all over it, you know? So the same as along this line, the drop is
4.
along this line, the drop is 4. So the pressure is 4. Not only the drop, the pressure is 4. So this pressure gives what? How to like if we have this pressure means what? It should gives us something else. Do you know what is that something else?
The flow.
At any point, this is the water pressure, right?
Head.
Head, which is the water pressure. So the water pressure has a significance. It has a different name. The name is hydrostatic pressure. So what happens in the hydrostatic pressure? What is the meaning of the hydrostatic pressure?
Actually,
What is the meaning of the
It's
hydrostatic
a-
pressure?
The
this
pressure.
triangular thing and distributed force is applying in a triangular way, and the equivalent force is 1/3 from the base. If we consider the area is unit,
The pressure applied by the water on any structure or the soil.
the pressure
Okay,
exerted by
but-
water on a surface.
Hydrostatic pressure means what? What is the meaning of the hydrostatic pressure? If you cannot tell me this, then I should deduct 5 points from everyone.
P equal to H rho G.
Any pressure created by water or something.
Like
Okay,
when the
that's
depth
hydrostatic pressure. Hydrostatic pressure. What is the characteristics of the
when
hydrostatic
the
pressure?
depth is increasing, the pressure is increasing.
It's a
No.
distributed pressure.
Is that simple water pressure due to gravitational force?
Hydrostatic pressure. What is Pascal's law?
In
Water
the
pressure is
height of-
same at a given elevation everywhere,
Water pressure is same in every direction.
in every direction, at a given
Right.
elevation, at a constant elevation.
So basically, if you have a certain point, on that point, the pressure distribution is equal in
All directions.
all directions, right? So means if you have a structure here, let's say you put a structure here, then what is going to happen? If you have a structure, then what's going to happen?
Like 7. If we
Yes,
assume that 7
so it
is
will also have an uplift force at that pressure because it has a downward force, also has an upward force, right? So if you have even in a push, that will push it back. Water will try to punch it up, right? Like a balloon. If you push a balloon, what happens?
it wants to go up back.
It wants to go back. So the same way, whatever the water pressure is inside the soil, that will try to push it up. That creates uplift force. You know, whenever there is a water, it creates a buoyancy. You know what is buoyancy, right? When you push the water, water push you back. That's the buoyancy, and that buoyancy is even same in the soil. You also have the buoyancy, right? So because of that buoyancy, now what is the pressure of that buoyancy? We get it here, H equal to 7, H equal to 6. That's our buoyancy force, because that's a hydrostatic pressure. It's equal in every direction, right? So that number push it up all the way. Is it clear?
Yeah.
Right? Do you get my point? So at every point, this is the water pressure, and that water pressure will tell us how much buoyancy force is pushing any structure up. So let's say instead of the sheet pile, now let's say this is our soil, and now we have a big dam here. Within the dam, we have a water table. It's a similar thing, H, you know. Now, how does our flow line looks like? So here's the water. What is our first flow line?
To the surface.
Our first flow line is here. Our last flow line
At the base.
at the base. So those are our flow lines. Now we also need to draw our equipotential lines. So let's our equipotential lines are. So what are our other flow lines? This is our first flow line. So basically our first flow line is this, you know, and this is our last flow line. So we have other flow lines. Goes like this. Right? And in between the flow lines, then we have the drops. So basically, let me pick another color. So these are all drops. So let's say we have a drop here. You know, it's going to cut each of the point at rectangle. Like this. You know, so how many flow line we have here? So
5.
flow line. So let's say I add another flow line here. Let's add
4.
another flow line. Is this okay? So I have
5 and F.
So in this case, I have the number of flow lines. Let me count. So my first flow line, 1, 2, 3, 4,
Mhm.
5. So our number of flow line NF equal to 5. How many drops?
14.
Okay, between this. So let's say our number of drops is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So in D equal to 14, right? So let's our H equal to 20. So what is the drop in each line?
20 over 14, which is
4.
1.4.
Okay, 1.4. So our each drop is H over ND, which is 20 over 14 is 1. Is it 1.4?
1.43.
1.42.
Okay. Okay. So this is the drop. So at each point we have the drop. So the pressure we can calculate at this point. So this is our how many drops? 1, 2, 3. 3 drops. So at this line, what is the pressure? The soil pressure at this line.
3 times
How
0.45.
so how we can calculate? So our total pressure was to H, which is 20 minus 3 drops multiplied by 20 over 14, right?
Right.
So basically this is 20 minus 3 into 1.43, right?
15.7.
15.7.
Uh-huh.
So this is 15.7 meter at this point, right?
Right.
So what is the water pressure here at this point? 15.7, right? What is the water pressure here?
15.7 minus 1.4.
1.4. What is the water pressure here?
Same.
Same, right?
I mean, minus.
Yeah, you just have to deduct it, right?
Yeah, the same process.
So basically, after all the deduction, what we can do is we can calculate how much pressure at this point, how much pressure at this point, right? And we can calculate what is the uplift force going up. So this is the uplift force, the water is pushing the soil upward, right? At each point, we can calculate this and we can calculate how much pressure water is pushing the structure upward, right? So this is the uplift force. Water is trying to push the structure up. So if the structure is pushing is upward, then what we have to find out? Something will have to push it downward, right? So who can push it downward?
Its own weight.
Its own weight, right? So basically, we need to make sure that it is having all the weight to be stable. Otherwise, it will be unstable. All right. Okay. So now let's look at the problem on the book. Where is it? Yeah. So there is a problem on the book, very similar. You know, I just wanted to give you the overall idea of how to do a calculation for uplift. You know, so for the calculation of uplift, yeah, I'm going really fast. You know, this is my second topic. I'm almost done. Today, I'm not wasting any time. So the uplift pressure is, let's look at the problem. So the problem is figure 5.27. What is figure 5.27? So the same problem that we did, right? So figure 5.27 is this one, which we did in the last class. So in the figure 5.27, we have our flow lines, right? We have our NF and ND. Oh, this is not drawn in this sheet. So that's why it's not working. Okay, let me try. I did it here. Yes. Okay. So this is how I did it in the last class. So let me erase it.
So when we take the uplift force, do we take the resultant force or we just take the distributed load
Which one? For
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 the
what?
for the uplift force?
We calculate at each point.
Okay, and then we
And-
just keep it at each point, or we do the like resultant.
Each point.
Okay.
The result, we first of all, we need to calculate at each point. And after we calculate at each point, then we will find out the load diagram, and then we calculate the total uplift force.
Okay.
After we know the total uplift force, we also need to calculate the total weight of the dam. And then from there, we need to calculate the factor of safety against uplift force.
Okay.
Okay. So basically what we have to do here is, let's say we know about how to draw a flow net. So I'm not going over it. So let's say we draw the flow net. So this is our step one for any uplift calculation. We need to have our flow net ready. So once we have our flow net ready, then what we have to do is we need to calculate the force at each point, you know, and this is a very good problem. This is a very good problem. That's why I picked this problem. So basically what happens, we have a H equal to 10 meter. In the other point is given. But in this type of problem, it's always better to find out the elevation. Remember it. Always convert it into elevation instead of the height. You know, because there is always an elevation difference. And if you have elevation difference, your pressure changes. You know, so basically in this diagram, you know, you have some difference in your height. So you get down. So basically we need to check if these are the same lines. Yes, it does. I didn't look at the problem before. Okay, so basically what happens, there is a height drop, right? So at this point, your total height is what? 10 plus this height, right? At this point. And then you have a drop. So here, let's say this height is 1 meter or 2 meter. So at this point, your total potential height is 12 meter, right? And within that 12 meter, let's say you have 1 or 2 drops, right? So from 12 meter, you need to find out the drops, not from the difference. At this point, what happens is maybe this difference is 1 meter, you know? So in this case, your total head difference is 11 meter, not 10 meter. So, and then from that 11 meter, you need to find out how many drops we have. All right. Okay. So
Okay.
basically,
Drop in the body of the dam, right? The concrete is going.
yes.
Oh.
Yes. We need to calculate the drop.
Okay.
So, in the figure 5.27, the cross section of which replotted in figure 530. So basically, the bottom part is given here. So this is the bottom part, you know. So just the bottom part of it. So with the one I just mentioned is 2 meter. Basically, this is 3.34 meter, and then this is 1.67 meter, you know, and this one is also 1.67 meter. So this is 1.67 meter, 1.67 meter, you know, and then 1.67 meter. Okay, give me one more second. Okay, so basically we have 2, and so we have a drop. So on top of it, we have a head. What is this head? H equal to what?
10.
10 meter. Who said it? Who said 10 meter? You did?
No.
Okay. Who said 10 meter?
Come on,
I
Sai.
said.
Yeah.
I said.
Okay, very good. Okay, so what is the total head? 10 plus 3.34 at this point, right? This is your head. You get my point? And then at this point, what is our potential? What is the number of drop at this point? So we have point D, E, F, G, H, I. You know? So let's go back to that problem again. Okay. So in this problem, this is D, E, F, G, H, I. Correct? So what is the drop at point D? How many drop? 1, 2.
2.
2 drops. And what is the loss, head loss in each drop?
13.34 over.
No. What is the head loss in each flow net? Along this line. This is our line number 2, right? Number of drop is 2, right? So what is the total drop? Our drop is always H over NF. ND, sorry, number of drop. So our H is what? H is the total head difference. You know, or del H. Let's put it like this, del H. So you have 10 meter and this is 0, right? So your del H is 10 divided by how many drops? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So your ND equal to 12. So your each drop is 10 by 12, right? That's your each drop. So what is the 10 by 12? Is 0.83?
Yeah.
So basically this is 0.83. Now you have 3.34, right? So this distance here is 3.34 and each of the length is what?
1.67.
1.67, right? 1.67 and here we have 1.67. All right. So now in point D, what is the total head? Point D, total head. 10 plus 3.34, which is 13.34 at point D, minus how many drops? 2 drops, right? So at point D, this is 10 plus 3.34. This is our total head minus 2 drops, and each of the drop is 10 by 12. This is our point D, right? What is our point E?
Dr. Khan is left.
Now I am the host.
Come on, continue, Dr. Saeed. Calculate it.
Dr. Fariha, go ahead.
Dr. Faria is cold, wearing 3 jackets.
What do you want to say, Omar?
I need to participate to answer the question.
Yeah, got it?
Somebody needs
Yeah.
to Dr. Khan. Let's see.
Yeah.
He's back. Dr. Khan is back.
Yeah, in my computer something happened and my computer just turned off completely. Okay, so it was under the battery power and the battery power was not working right. But the interesting thing is Zoom is still working. Okay, give me a moment. Let me switch my computer, okay? I can make someone host, so it stays like this. Okay, let me make Omar host. Assign, make host. Okay, so I can leave. And let me join in from another computer.
Okay. Plus
Dr. Omar.
5 grades plus for every student. Instead of the 5 we lost.
Can you hear me?
Yes. Yes, we can hear you, Dr. Khan.
Okay, I'm trying to connect the earphone. everything is losing charge, and I have no idea why it's giving me a hard time. And because the airport has a very good noise cancellation, you know. But it's not connecting. I think I need to restart my computer. Still, the sound is not working. Okay.
AirPods is not connected.
No, AirPod is still not connected. AirPod is giving the problem. Oh, microphone. AirPod. Okay, I don't know. Okay, as long as you can hear me, I think it's fine. Let's move on. Okay. So basically what happens here is we are looking at the point B, point E. So what happens in the point E? So point E, it should be, what is the number of drop in the point E? And
One.
what the level?
It's the same level, 13.34, right? But it got just one.
Yeah, so this is 13.34. So this is 13.34 minus
3 drops, right?
minus 3 drops. So 3 multiplied by 10 by 12, right? So you get a number. What happens to the point F?
It becomes 13.34 minus 1.67
Okay,
minus 4 times
4
10.
minus 1.67 minus how many drops in point F?
We got one. So it's 4.
Okay, so point F is here. Okay.
So still 3. Still 3 times.
No. 3 is here. 3 is here, 4 is here.
2.5 something.
Interpolate. So it's 3.
Yes, interpolate. So maybe this is number 4, right? 1, 2, 3. So maybe 3.3, you know, maybe 3.3, something like that. So maybe 3.3. So minus 3.3 into 10 over 12, right? Like that.
Yeah.
And what happens to the point G? Point G is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this 9 point something, maybe 9.6, right?
Yeah.
So PG will be the same, but minus 9.6 multiplied by 10 by 12.
I have a question.
Yes.
Should F be from 13.34 or
No. You look, the G is at this level, right? So this is 13 minus 1.67. You know? So, and then H is again 13.34, right? I is also 13.34. So basically, if we go down there, the numbers are already been calculated. So I'm not going in all details. I'm just going to look into it. So it's already been calculated pressure at E, you know, pressure at F. We consider 3.3. They consider 3.5. Head at G is 10.67, which is 3.34 minus 1.67 is the same thing. So 10 plus 1.67 minus we considered 8. 8.6. They consider 8.5. Then the next one is 9/10/12 and 10/10/12. You know, that's it. So basically, you get all the numbers. So you calculate it, put it here. You know, plot this diagram. Now, what will be the total force? What will be the total force? Any idea?
Yeah, of the diagram.
Which diagram?
The diagram of the pressure head.
The total force is the total pressure head, right?
Hmm.
So the total force is going to be what? How do you calculate that? Basically, the question I'm trying to ask is, how do you calculate the total force? This is a distributed force, right? You understand that?
Yeah.
So basically, it's a pressure distribution. This is a pressure, and this is a pressure distribution. So we need to calculate the force. So to calculate the force, we need to calculate the area. You know? So once you calculate the area, that will give us the force per linear feet or per linear length, right? So basically, we need to calculate the area of each of it. So this, let's say A1, A2, A3, A4, and A5. Okay. So we know all the length. You see 1.67, 1.67, 18.32, 1.67, 1.67. So all is given. And we know all the length. So these are trapezoid. So what is the area for trapezoid?
H1 plus H2 over.
No.
To H.
How to calculate the area of the trapezoid?
Half into two side, addition of two side into the distance.
Okay, half into the addition
Length
of
of the
two parallel lines.
Parallel lines into the distance.
Okay, so this is half multiplied by 11.67 plus 10.84 multiplied by the distance 1.67, right? So this is the area. Okay. So this is the area. Then what is the total pressure? Total force. So that's why they're calculating it. This is basically your gamma H, you know, when you're trying to calculate the force. So you know the head multiplied by the gamma H, gamma. So you get the gamma H. So multiplied by this, so you calculate all of it, you get the total head, right? So this is your total head. So this is your uplift force. This is your uplift force. What is the factor of safety against uplift? And how do you calculate your factor of safety against uplift?
The weight of
the gram.
we calculate the equivalent force of the weight over this uplift force.
Yes. So what is the definition of factor of safety?
The resisting forces over the acting forces.
Okay. What is the
Friends over enemies.
friends over enemy? That's it. So this is your friend. This is your enemy. So what is your enemy?
Is the uplift force.
Enemy is the uplift force, which is 1714.9. What is your friend?
The weight we calculate as force.
Okay, so we need to calculate the weight, right? This is not there. This is not calculated yet. So how you can calculate that?
The same way we calculated the uplift force, we divide it into areas. We multiply
So
it
we divide it into areas, right?
by gamma concrete.
Multiplied by gamma concrete. That's it, right? So we calculate that. We have the area. We have multiplied with the gamma of the concrete. We get the total pressure, right? So we get our friend. So once we get our friend, then we have to calculate the factor of safety. And how do we make sure that this is safe against uplift?
It's more than one.
Is it more than one? What is the factor of safety we record for uplift?
Not sure what's the number, but I would say more
The number is 2. I think the number is 2. But can I check that?
I can check that really quick.
The factor of safety against uplift is very likely the number is 2.
I think it's between 1.2 to 1.5.
Uplift, that's very low. Uplift is usually higher. So you need to have the factor of safety against uplift, factor of safety against piping, and factor of safety against then the bearing and all other calculations. We also need to check the factor of safety against bearing, right?
Yeah. Sliding, bearing, and overturning, right?
Yes. So do you need to check the factor of safety against the sliding for earth dam?
We should. I mean,
Yes or no?
yes.
Or it's a requirement?
I know for retaining wall, yes, but for earth dam, no, earth dam is no, it's earth, so it can't slide.
It can slide. Earth dam also can slide if you have a washout. Earth dam can slide if you have a washout. Remember that, right? So let's say you have a seep, you have a overtopping. So if you have a overtopping, it will going to lose the materials from the top, right? So your thickness is shrinking when you're losing the material, and at one point your weight is not enough to keep the water pressure. It will just go away. You know. So when you have an overtopping, you don't see the entire soil is washed out. You see partial soil washed out, and then the second section go away, because then after a certain washout, the rest of the part is not heavy enough to sustain the water pressure. So then you have the sliding failure.
But usually it's too high, the sliding, the factor set for sliding.
Yeah, it says usually for earth dam, the factor set is usually too high, so you don't need to calculate that most of the time. The same goes for the exit gradient and other things, but we are trying to discuss that, right?
Yeah.
So that's the factor set against uplift, and then we also need to find out the safety of the hydraulic structure against piping. So that's our last topic that I'm going to cover today. Okay, as long as we are done, we're done for the class. So I'm not taking any break. Okay. So there are few methods to calculate the factor of safety against the piping. You know, so the first thing is what we have to do is we need to find out the upward seepage occurs. We have to find out the hydraulic gradient, and we have to calculate the critical hydraulic gradient. You know. So the factor of safety against piping is if our critical gradient is I critical is greater than the I exit, then we have a piping failure. So what is I exit? Any idea what is I exit?
This is the hydraulic gradient at the other side of the structure when we have at the end of the flow nets.
The exit gradient is always like, let's say you have the dam, you know, and so you have different flow lines, equipotential lines, like this. So the one at the end, at the exit, that is your exit gradient.
The last, okay.
The last one. The exit gradient is where the water is coming out. So if you have a very high pressure at that point, you always have a piping, because now you'll see the bulging and water is coming out, you know.
That's a very common problem. So that means you have a lot of pressure over there. You need to take care of that pressure. Otherwise, you always have a washout. That's create the soil boiling, sand boiling. So sand boiling is always there. What happens in the sand boil? You see water is coming out, soil is bulge, right? It's coming out. So that's your sand boil. Sand boil is the perfect example of the piping and the problem with the exit gradient. And if you see there's a problem in the exit gradient, then what you have to do?
You need to solve it. You need to like make a cutoff or berm or
You need to make a cutoff berm or
relief wells. There's different solutions. Increase the, like put a clay cap at the other side. The sand boil side.
Well, in terms of that, what happens is your earth pressure is coming out, right? So you always have a pressure coming out. So if you have a pressure coming out, then what happens?
You will have erosion, and then
You have erosion. So what is the best way of taking care of it?
well, it's it depends case by case, like how
I got it, but what is the best possible way to solve that problem?
reduce the head on the
Release the
water.
head, release the pressure. You know how eagle fights with snake?
Just
Any idea?
cut the head.
No. No. How eagle fights with snake? Do you know?
That's a good rule.
Any idea? Anyone?
It irritates the tail.
No. If you irritate the snake in the tail, then you're inviting the snake. You're making it angry. You never win. That's not a good idea at all. So how you win?
To make the snake blind about its surroundings.
Okay, very good. It's close. So what eagle does? Eagle take the snake and put it on the air.
Nintendo Art. Super
So what is the winning formula of the snake? How snake fight?
If it's on the ground,
If it's in the ground, it can have and it can bite, right? It needs a support structure to bite. If it doesn't have the support structure, snake has nothing to do. Snake has no energy, right?
Yeah.
No strength. But eagle will always win because that's the strength of the eagle. So how you can win this?
first, we reduce the pressure and then we'll find the
We reduce the pressure. So how we can reduce the pressure? Who is helping water to retain the pressure? Hey, go to sound. Right.
the earth dam.
Dam itself. The height of the water.
How we can win?
Increase the weight of the dam.
How water keeps the pressure?
Well, the pressure depends on the height of the water.
Because is always a pressure flow, right?
Yeah.
So for the pressure flow, to keep the pressure, what do you need?
You need the height.
You need the confinement. If you don't have the confinement, you don't have any pressure. Water holds the pressure when water has a confinement. If you release the confinement, you release the pressure.
So we open the spillway.
So what you need to do here is you need to have some kind of filter layer. So the filter layer has big voids inside. So water comes in and then it doesn't get the same confinement it used to be. You know, so if you take the confinement out, you take the pressure out. Because it doesn't get any reaction. Snake has the power, but if the snake is in air, snake cannot bite because snake doesn't get the confinement. Snake cannot get anything to hold. So it releases the pressure. Really bad example, really different example for this, but I feel like those are similar. The ideology is similar. You know? Anyway, so that's that. We should discuss that later. It's not our target today. Our primary target is to discuss about like the factor of safety against the piping. So if I want to calculate the factor of safety against piping, all I have to do is I need to find out the I critical and the I exit gradient, and we can go from there. So now the question is, what is the I critical? So the I critical is the formula, which is the gamma prime over gamma W. Okay. So what is gamma prime?
Is the effective unit weight, the soil unit weight.
Yeah, it's the soil unit weight, and then the we have the I critical. So sorry, this is the I that's the I critical, and then I exit we calculate it from the flow net, and from there we calculate the factor of safety. That's the easiest way to calculate the factor of safety against piping, you know. So this is a direct method of calculation. Then there are several indirect methods. So the indirect method are, you know, this is the lens method. So in the lens weighted creep distance, the weighted creep distance, you can also calculate the factor of safety against it. You know, so it has like some guided method, and then from there we can calculate. So what we have to do is we need to calculate the weighted creep ratio, and if the weighted creep ratio is within a certain level, then we can say it's safe against piping. You know, but those are empirical method, and those are old method. It's not very much used, but it gives us some idea. You know, so basically the best idea to find out the factor of safety against piping is this one. You know, factor of safety is we need to find out based on the critical exit gradient. Is like the critical hydraulic gradient with the exit gradient. Okay, give me one. Okay, now the third one is so this is the third one. So the other one is the factor of safety against heave, and this is the one proposed by Terzaghi. You know, this is the one proposed by Terzaghi. So this method is, let's say we need to calculate what is the weight. We need to calculate like what is the U, the pressure at that point, you know. So this is what we need to calculate, the U. So we are trying to find out the factor of safety against heave, which is the same as the piping. So if there is a heave, you know, for example, in the sand boil, you see a heave. So if there is a heave, means your end pressure is too much. That's why it's creating the heave. All right.
I think, Dr. Khan, I think
Dr. Khan, I think
your screen is stuck.
It is frozen.
Yeah, it's still at the factor of safety for exit.
Oh. Yes. So the last one is that so are you able to see this one? The factor of safety against the weighted creep method?
Yeah.
So in the weighted
Mhm.
peak method, we have this. Okay, so the last one is the Terzakis one. In the Terzakis method, we need to find out the factor of safety against heave. So basically, what we have to do is this is the factor of safety against heave. So we need to calculate the weight. So we need to consider a soil prism. You know, we need to find out like what is the weight of the soil in the soil prism, and then what is the uplift force of the soil on the soil prism. So if the uplift force is higher than the weight of the soil, then we'll have a heave. If the weight of the soil is higher than the pressure coming from the water, then there is no heave. You know, so basically what we have to do is we need to find out the U. So to do that, what Tarzaki proposed is, let's say we have a sheet pile, you know, so we have a sheet pile. So what we need to look at is we need to find out the D, and then we have to find out the 2D. So the D is the depth of the sheet pile. Okay, so this is the D. And then we have to consider like D by 2. So this is here. So basically this area is our influencing area, which is going to give us the resistance. So, and then we need to find out like how much pressure is coming from the water and pushing it up, you know. So this is pushing it up. So we need to find out the U, which is the pressure pushing it up, and the weight of the soil is pushing it down. So the weight of the soil is like the area. So the area is D multiplied by D by 2. So that's the area. And then we need to find out the unit weight. So the unit weight is gamma prime, not gamma, right? Why gamma prime?
Because it's submerged, so it's effective unit weight.
Okay, but why submerged? Why we need to consider submerged?
Because we are below the water.
Water level is
Already we have a high head on the other side, on the protected side, right?
On the protected side, what we have?
we have water head on that side, so most likely the soil is saturated to the surface.
Okay.
But being more conservative, having like assuming that the water is at the surface of the ground. So
Okay, I got it. But why we are considering gamma prime? We are considering gamma prime because the water is pushing it upward always. So that balance out the weight of the soil. Okay. So and then so this multiplied by gamma prime, so you get the W, right? So the weight, and then what is our U? So in this case, U is the pressure, you know. So use the pressure. So how we can get the pressure? We need to calculate like the exit. These are the points coming from our flow net, you know. So from the flow net, we get the water pressure at different point, and then we calculate the average H, you know. So you can calculate the pressure based on like weighted method, or you can just average it. That's fine. You know. So you'll have like a small difference if you do the weighted average method, or you can just do the normal average. You know, you find out all the numbers and just do an average of it. So you get a HA, so which is the pressure coming from the water, and then multiply with gamma W and D. This is your head. So basically you need the area, you know. So D by 2 is your area. So you basically, this is gamma WHA multiplied by area is D by 2 into 1. That's the formula, you know. So this is the area, and this is the force. So once we get all this too, we just plug in these numbers, and we get final equation is this: D prime D over gamma prime and H over gamma W. Okay, so so from there we can calculate the factor of safety against piping, you know. So these are the three methods. So the first method is the critical exit gradient. The second one is the Lenz method, and the third one is the Terzakis method. You know, three methods. And so there are some problems on this. I think it's the same problem. Flow net of a single, so 5.26. So the 5.26 is, I think that that's the same, the first problem that we did.
So D in the Terzaghi method is the depth of the sheet pipeline, the embedment depth, right?
D is the embedment depth, yes.
What if, I mean, can we calculate it if it's an earth dam or concrete dam without, there is no sheet pile or something, so.
No, we cannot. Then we need to use the exit gradient method.
So it's just for sheet piling,
It's just for sheet pile.
okay.
Whenever you don't have it, then you just have to calculate the exit gradient. So let's say in this problem, or 5.26, right? So what is the 5.26? It's still. Yeah, it's right here. This is the 5.26. So, just let me see. Okay. So basically, if you take a look here, this is our D, right? 1.5 meter. And so D by 2 is 1.5 by 2 is 0.75. And in this point, we have a pressure head. So we need to find out like, what is the pressure head at this point? So we need to calculate D by 2, which is 0.75, right? So within the 0.75, we need to find out like, what are the water pressure? So 1, 2, 3. So point C, then another point, then another point, you know? So we have like 3 different points, and each of the point we can find out like what is the water pressure. So the first point is 2.5, 1, 2, 3, 3 drop, right? So 2.5 minus 3 drop, and each of the drop is 3, right? On this level is 3. So sorry. So 3 minus 3 multiplied by 2.5 over total number of drops. So 1, 2, 3, 4, 5, 6. Right? So basically the first point is 2.5 by half is 1.25. So basically this number is 1.75. The second point here is drop number 4, right? The middle point. So this is 3 minus 3 into, sorry, is 4 multiplied 2.5 by 6. So basically that number is going to be how much? Can you calculate? So this is 2, so this is 5 over 3. So 1.67. So 3 minus 1.67 is 1.33. So this is 1.33. So this is 1.33. And the third point is right here. So that 1.33 is going to be, this is 4. So this is, let's say 4.2, you know. So 3 minus 4.2 multiplied by 2.5 by 6. So this number is what? Maybe
1.25. 1.25.
So 1.25. Okay. So this number might be a little bit different, you know, and that is perfectly okay in your calculation. So this number might be a little bit off because you're using a graphical method. So you may read it 1.4, someone may read it like 1.6 because there is an eye approximation. So there is always a chance of having a different numbers, and which is okay. Anyway, so if we take a look at that, we will get these 3 numbers. So this is the exit gradient. I'm going there. These are the 3 numbers. So basically it got 1.5 to equal to 1.5, but it calculated 1.15, 0.83, and 0.75. I don't know. Let's take the number. Okay. I just wanted to show you how to do the calculation. So I think these numbers are okay. So I'm just rely on that. So based on that, we can get the HA is equal to 0.917. All right. So once we get this number 0.917, we get to the HA, and the rest of the thing is pretty easy. All we have to do is we just need to plug in these numbers. Yeah, this is how they calculate it. 2 by 6 and 1.8, you know. So basically that's fine. So we get a HA and then we calculate the factor of safety, which is 1.7. So then there is another calculation, which is the exit gradient method. So for the exit gradient, you just need to calculate. This is very straightforward. You know, you need to calculate the exit gradient, and you need to calculate the I critical. So the I critical is gamma prime over gamma W, which is given. You know, and then the exit gradient. How you calculate the exit gradient? Not like this. You can calculate the exit gradient like this. This is how you do it. You don't need to use the theoretical equation. Forget the theoretical equation. Exit gradient you should calculate based on the graphical method. So your end exit gradient is what? On that point, 3 minus 0.5, which is 2.5. 2.5 by 6 is the del H, right? So basically your del H is your exit gradient, right? That's your last drop.
Yeah.
You get my point? Your exit gradient is your last drop. So is your number of drop, your total pressure head divided by the number of drop is your exit gradient, right? So basically you can calculate the, sorry, that's your del H. Sorry. I was wrong. So this is your del H. So exit gradient is del H divided by the length.
Yeah.
So del H divided by the length. So the length, how do we calculate the length?
It's just the horizontal length from the beginning.
So
From
how
the
do we
first
calculate
corner,
that length?
the first corner to the,
Yeah, let's go there. Let's do it. Where is it? Yes, so in this one, what is the length?
0.82 they calculated, which is the
Length, right?
difference. Yeah.
How do you calculate it? Calculate this length. You need to use n scale, and then you need to calculate using this scale.
That's the distance between the last drop with the surface, right?
Yeah, the exit gradient at the first one, you know, where the water is exiting, the first one, not here. But it should be the same thing. The exit gradient here, no, it's not going to be the same thing. Here the pressure drops. Because here your L is higher, you know. Your head difference is same, but L is higher. But in this one, your L is lower. So exit gradient you need to calculate for which one you have the lowest L. You know, which one you have the lowest L. So basically from there, you get a factor of safety against the, you calculate the exit gradient. So basically, you know that the head difference, which is your number of drop divided by the length. The length you calculate it based on the graphical method. So you use a scale or ruler, and based from the ruler you find out like what is the length, and look at the scale. So find out that number, you know. Nowadays it's very easy in the Adobe Acrobat Professional. In the PDF, you can do that. You don't need a ruler. So you can just use the ruler command on there, and they have a scale. So you can set the exact scale, and then you can calculate that. That's very easy. You can do that, and it's pretty accurate. Most of the civil engineering drawings doesn't give you all the dimensions. So you have to use the graphical method. So that's why all the civil engineering drawings are in scale drawing, right? So you need to look at that, and based on that, any distance is missing, you need to use the ruler to find out what is the distance. So in this one, you also have to do the same. You just need to find out the exit gradient. You need to find out the length at the last one, find out the exit gradient, find out the factor of safety against piping. Okay, that's all. That's all I wanted to cover. Thank you. Any question? Oh, there is another problem. Let me do that problem. So the lens method has another problem here. What is that? Yeah. So the dam section is 5.45. So the 5.45 is here. Yeah, this is the 5.45. And in the lens method, we need to calculate the weighted creep ratio, and based on the weighted creep ratio, we need to make the decisions. So basically what is given is the subsoil is a fine sand, right? And in the fine sand, it says using lens method, determine whether the structure is safe against piping, So that's the lens method. So all you have to do is we need to calculate the LW. And then once we know the LW, this is we need to calculate the weighted creep LW divided by the head difference, which is same as the exit gradient, right? I exit. In other words, you know the length divided by the h,
And then we compare.
It's basically inverse of that. It's the inverse of that. Lens method is just the inverse of it. Anyway. So the formula is you have to calculate all the length along the vertical and along the horizontal. So the formula is along the horizontal, your drop is less, So, and you have to calculate the actual drop. So let's say you have an apron. So in the apron, so this is the distance 6 meters, then you drop 1 meter. And then you drop 8 meters. So here you drop 9 meters. And you come up 8 meters. So you have to calculate all the length. And then you go another 10 meters, but here you drop 1 meter, you move 10 meters, and you come up all the way. So all you have to do is add all the vertical distance, add all the horizontal distance, So the horizontal distance is 6 plus 10, right? That's your horizontal distance. Vertical distance, what do you have? First 1, 8, down, 8 up, right? Then here is 1 down, 2 up, right? So here 1 down and 2 up. So you know the LH, LV, so you calculate the LW, right? So once you calculate the LW, this is very simple method. So divide by the head difference. So here you have 10 meters, here you have 2 meters. So 10 minus 2. And you have the LW, so you get the number 3.17. All right. So once you have the number 3.17, you need to make the decision. So we need to go back on the table again. What is the table? Yeah, this one. So this is a fine sand, and the number is 7. So we want, this is the minimum number, so 7 or higher,
So it's not safe.
It's not safe, right? That's it. You make the decisions that it's not safe against the piping failure, right? So what is their requirement? Yeah, this is about 7. Creep ratio is 3. The structure is unsafe. We make the call. That's it. That's all the problems. And then in the next class we'll do flownet, and we'll done with the flownet in the next class. That's it. So and in the next class we are done with all of our calculations. So everything that we are doing is good enough to do the seepage calculation for any earth dam, and doing the hand calculation against the piping, against the factor of safety, against the exit gradient, all of it, the seepage volume, everything we can calculate out of it, So that's pretty much it. Any question?
No. So we got the homework
Yeah, the homework is posted, and homework is due next Tuesday. Submission is online.
Okay.
Okay.
Okay,
Okay. Thank you.
Thank
thank you so much.
Bye.
Bye.
Thank you.
So next class we are meeting on Tuesday
Okay.
in class. Same time.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.